Okay, I'll give it just a minute so you guys can scan the exam that we'll be going over today. It'll be 2006. And in the meantime, so if anybody needs to break their fast on Friday for Ramadan, you will get, I think it's about 5 minutes at sunset. The TAs will announce that. So you'll take that time to go break your fast. And then at the end of the exam, you'll get that time back. So if it's like 7:35 or something, you get up, take your break, get back at 7:40. You'll get till 8:05 to finish your exam, or whatever, you know, whatever time it is. It starts at 7. I don't remember what time it goes to, but. And I guess I'm just going to go ahead and get started. So if you're joining us late, then you'll just do the 2006 exam. And so we're going to start with nomenclature. So for nomenclature, we are learning our aldehydes and our ketones. And then we'll also learn our benzene common names. So some of these are not necessarily functional groups that we've fully explored yet, but they are going to be on the exam, or potentially on the exam. So I made a list for you guys. So this is your exam 2 nomenclature list. So at the top, this is like a full list of all the stuff you'll learn by the end. So I highlighted just the exam 2 material. And then at the bottom, we have the common names of benzene that you'll need to know. So just real quick, we'll look at those. So we have benzene, obviously, toluene, which has methyl, phenol with the alcohol, benzaldehyde, which is the 1-carbon aldehyde, and then so on, so on. So make sure you guys are familiar with this, because if you get a common name on your benzene, then you'll use that as your parent, and then the rest will be substituents. One other thing that I especially like to point out is phenol and benzyl. So these ones are very similar because it just has to do with where the benzene is as a substituent. So these ones can be kind of tricky because they're really similar. So phenol is if the benzene is directly attached to the main chain, and then benzyl would be if there's an extra carbon in between the main chain and the benzene as a substituent. All right, so let's just go back and get started with our nomenclature. So for this first one, we have an OH, we have a carboxylic acid, and we have kind of a long chain ketone. So in this case, there are 2 potential common names that we could do. We could do phenol with the alcohol, or we could do benzoic acid, which is the benzene with carboxylic acid. So if you look at the priority list, again, we haven't fully learned all of these, but carboxylic acid has a higher priority than an alcohol. So that's going to be our common name for this benzene. And so whenever we choose a substituent to be our common name parent, it's always going to be carbon 1. So then we have our 2 substituents, the OH and that longer ketone. And so we'll have to do the nomenclature for those. So just real quick, our parent is benzoic acid. All right, so then we just have our subs that we need to do. So we have a phenol, right, or not phenol, sorry, a hydroxy, since that alcohol is a substituent now. And we have a 1, 2, 3, 4 carbon chain. So that would be a butyl. And then whenever we have a ketone as a substituent, it's going to be the oxo name. So that ketone is on carbon 3 of that butyl chain. So this would be 3-oxo-butyl for that substituent. It's a complex substituent because it has a substituent of its own, that oxo group. So we'll put that all in parentheses. And so now we just have to figure out the numbers for the substituent. So if we start at our carboxylic acid, if we go counterclockwise, we will get 2 and 6 for our subs. If we go clockwise, you'll notice that we get the same numbers, so 2 or 6. So whenever we have a situation like that where the subs will get the same number either way, we'll then move to the alphabet priority. So in this case, we're going to be looking at the H of hydroxy versus the O of the 3-oxobutyl. So H comes first in the alphabet. So we will go with the red nomenclature to give that hydroxy a lower number. And the butyl group will be on carbon 6. So we don't have any stereochemistry that we have to worry about. So we just throw this all together. So we have 2 hydroxy. Then we have 6 parentheses 3 oxobutyl. And then our parent name was benzoic acid. Any questions on this one? That's a great question, actually. So whenever we have the ortho-para-meta nomenclature, that's if you have 2 substituents on the benzene. In this case, we have 3. So ortho-meta-para is kind of like cis and trans. It's referring to the 2 different groups to each other. So you can't say, I have this group that's ortho to this and meta to that. It just doesn't really make sense. So in this case, we just do the numbers. If you were given 2 substituents, so maybe something like this, so you have something there and something there, you could do ortho-meta-para, or you could do the numbers as well. Sorry? Either or. So you could say this one is para, or you could say this one is like 1, 4, whatever the groups are. If one of them was like a common name, then you just say 4-methyl benzoic acid or something like that. Okay, I'm going to move on to the next one. All right, so this next one, we have an example of what I was talking about with the phenyl versus the benzyl, so we'll get to that. In this case, we have to number the carbons on that chain to see if it's longer than a benzene. If the linear chain is longer than our benzene, we're going to use that as our main chain, and then the benzene would be a substituent. So in this case, I'm just starting from the left because I feel like it. We might have to change that, but you'll see that this one is a 9-carbon chain. Benzene is obviously 6 carbons. So in this case, the linear chain wins, and that will be our parent. And I'm just going to number it the other way in case we need to compare. All right, so with our parent name, we have a ketone and we have a double bond. So in this case, the higher priority group is going to be our ketone. So we want to give the ketone the lower number possible. So with the orange nomenclature, we would have the 3 ene and 6 one. For the red numbering, we'd have 4 one and 6 ene. So even though the numbers are overall lower with the orange, the ketone is our priority. So that's why it gets the lower number. And so that means in this case, we're going to be going with the red numbering. So our base, I guess you'd say, is the non-ane. And then whenever we have alkenes, alkynes, and ketones, you number it like ene, ine, one. So if you have a double bond, a triple bond, and a ketone, you do number ene, number ine, number one. So we don't have an alkyne in this case, but that just means for our numbers, we're going to have non-6 ene and 4 one. So that's going to be our parent. So then doing our substituents. In this case, everything on the linear chain is accounted for except for this group right here. So we just have a benzene and we have a CH2. So remember that with a CH2 in between is benzyl, and with the benzene directly attached to that main chain, it would be a phenyl. So in this case, it's not in line angle structure, but we do have that CH2 in between. So this is going to be a benzyl group. And it's at carbon, here, let me, what's that? Either way, it didn't matter. But our number is 5. So this would be a 5 benzyl. We don't have any more substituents, but we do have to consider stereochemistry in this case. We do have a double bond. So in this case, we have 2 hydrogens and 2 other substituents. So the easiest way would be to do cis and trans. And in this case, since the hydrogens are opposite to each other, we could say this is trans. If you wanted to do it the E and Z way, on this side, hydrogen is obviously not going to be our priority. On the other side, again, hydrogen is not our priority. So these would be on opposite sides. And so that would be E. So you could do trans or you could do E. All right, so now we just have to put that all together. So we've got trans, 5-benzyl, and then non, 6-ene-4-one. Any questions on that one? Mm-hmm. So since ketone is our highest priority group, we're going to give that one the lower number. So that's what you'll do whenever you have a priority group. So even though we could get a lower number starting from the left, lower numbers overall, I mean, starting from the left, we need to give the highest priority group the lowest number. So that's why from right to left, we get 4 and 6, but the ketone is the lower number. Oh, that's because it's kind of like an alcohol. So it could be anywhere on that chain. It's going to be the priority, but we're not going to start from the alcohol because it may not give us the longest chain. If that makes sense. Yes. Yeah. Yeah. So it could be 6 non-ene-4-one. Okay. I'm going to go ahead and move on. All right. So for this last question, so this one we have an aldehyde, and so if you go to our priority, aldehyde is one of our higher priority groups. So in this case, we are going to first see the length of the chain that we can get with that, and then we'll compare it to the benzene again to see which one is longer. So for aldehydes, you'll always start with aldehyde on carbon 1 because it's the higher priority group, so we want to give it the lower number. And since it's on the end of a chain, we can always give it 1. So this aldehyde would be 1, 2, and then going to the left would give us lower numbers, so I'm just not going to go that way. 3, 4, 5, 6. All right. And then our benzene is going to be 6 as well. So in this case, they're both the same number, but since we have an aldehyde on the linear chain, we're going to go with that as our priority. All right. And then again, we always want to give that aldehyde carbon 1. So my numbering is already good to go in that case. So for our parent, we have a hexane as our base. And then the aldehyde ending is just going to be Al. So hexane becomes hexanal. And then since aldehydes are always going to be on carbon 1, we don't have to say 1-hexanal. It's always assumed to be on carbon 1. So you don't need the number. You just need the name of it. All right. For our subs, we have a group coming off of carbon 2. So 1, 2, 3. So that's just a regular propyl group. And that's coming off of carbon 2 on the main chain. So we've got 2 propyl. We have a benzene at carbon 3. And so again, looking back, benzyl versus phenyl. In this case, the benzene is coming straight off of that main chain. There's not a CH2 in between. So this one is going to be a phenol. All right. In this case, we don't have any stereochemistry to worry about. So we're just going to put all this together. For our subs, remember that we always put them in alphabetical order, not numerical order. So we have P, so that's the same, R versus H. So phenol will get the first position in our full name. So 3 phenol, 2 propyl, and then our parent was hexanal. All right, any questions on nomenclature? Okay, going to go ahead and move on. Real quick, if you guys want to take a picture of this, I'll give you a second. Yeah. All right, so moving on into facts. So this is an older exam, so it might look a little bit different, but I think generally the questions are the same. Did you guys get a frequency or wavelength question for conjugation on your first exam? No? Okay, so I'll go over this. Okay, so for wavelength, you could also be asked frequency. For conjugated systems like this, it's asking us about like this pi to pi transition in the UV spectrum, but basically we're looking for conjugation and we're looking for R groups on our double bonds. So conjugation will lower frequency. And if you remember from physics, frequency and wavelength are inversely related. So if this decreases our frequency, it will increase our wavelength. And so there's a specific number for conjugation and additional R groups. So I think conjugation, I think it adds about 40 nanometers for the wavelength, and additional R groups on the double bond, I think it's about 5 per group. So if we had 2 conjugated double bonds, let's say that's 40 because there's 1 conjugation, and then 3 conjugated double bonds, there's 2 conjugations, so it'd be 80. So the bigger factor is conjugation. So the more conjugation we have, typically it's going to be better. But then the number of R groups could also actually influence it as well. So we'll just do the question so you can kind of see what I'm talking about. So in this first structure over here, we have 3 conjugated double bonds, the alternating double bond, single bond, double bond pattern. So I'm just going to write 3 conjugated bonds. In the middle, we only have 2 conjugated double bonds. This one over here, there's an additional single bond in between that pattern. So this one we would not consider to be conjugated, just the 2 on the left. On the right, again, we only have 2 conjugated double bonds. This one is too far away from the others. So already we can determine which is going to be our greatest wavelength. Again, more conjugation increases the wavelength. So on the left, we have an additional conjugation. So that's going to give us basically an extra 40 bonus points, 40 nanometers. So this is going to be on the left, our longest wavelength. So between the middle and the left, I mean the right, sorry, the middle and the right, I'm going to go ahead and look at the number of groups I have for each of those double bonds. So in this one, we have a mono subbed double bond, we have a tetra sub double bond, and we have a di subbed double bond. On the right, we have a tri, we have a tri, and a di. All right. So remember that each R group is about 5 nanometers. So I'm just going to go ahead and count these all up. So mono would be 5. Tetra would be 5 times 4, which is 20. And then di would be 2 times 5, which is 10. Tri, so that's 15. Tri, which is 15. And di, which is 10. So in the middle, we have 35. And then on the right, we have 40. So it's a very slight difference, but the group on the right is going to be just slightly longer in wavelength. So it's going to get our number 2, and the middle is going to be our shortest wavelength. Any questions on this one? No. I would suggest doing it with like the 5 nanometers, because if you count these up, 4 plus 2 plus 1 gives us 7. I mean, I guess you're right. 6, so 8. Yeah, I guess so. Maybe you could double check with the 5, but it's up to you, I guess. I just like doing the 5 because it kind of gives me a concrete number. Okay. Moving on to the next question. So this question is about electrophilic aromatic substitution. So we just kind of learned this one. So remember that for EAS, we want donating groups. So for EAS, we first have a group that attaches to the benzene that produces a positive transition state around that benzene. So we want donating groups to kind of donate their electrons and stabilize that positive charge. So I would suggest going back to chapter, what is it, 17? 17. I think there should be a chart of like the increasing donating and deactivating and like all that stuff. So I recommend looking at that and kind of familiarizing yourself with it. But we can go ahead and just take a look at these. So on the left, we have what's called an amide. It's kind of like an ester, except the oxygen, the single bonded oxygen is a single bonded nitrogen instead. In the middle, we have an amine, which is just a nitrogen with some R groups. And then on the right, we also have another amide. So starting with the left one, this is actually going to be considered a withdrawing group. And the reason for that is because our electron density is moving away from the benzene ring. This amide can do resonance, but it's not towards the benzene ring. All the electron density is kind of going away and towards the nitrogen and that oxygen right here. So this is actually a pretty strongly withdrawn group. In the middle, we have an amine. So amines are very strong activators. On the right side, we just have some hydrocarbon. So we can do resonance with the benzene ring with that nitrogen lone pair. And so we can resonate all sorts around the ring and donate that lone pair towards that benzene. So that's going to be a donating group, and it's very good. On the right, we have another amide, but the difference is the nitrogen is actually attached to the benzene. So this one's slightly different than on the left. So we are kind of donating towards this, this carbonyl, but we could also donate towards the benzene. So we can donate towards the benzene. So this one would be technically a donating group. However, because we're kind of splitting or sharing that resonance with the carbonyl, it's not going to be as good as just the regular amine. The amine doesn't have anything on the right over here to take away that electron density. There's not like any resonance or anything going on to that side. So in this case, the amine by itself is going to be the strongest activator, strongest donating group. So it'll have the fastest rate. On the right, we have a group that's donating maybe half towards the benzene and half away from the benzene. So this would be our second fastest. And our slowest is going to be the amide with the nitrogen away from the ring. because all that electron density is kind of being taken out of the ring and away from the benzene. Any questions on that? So on the right, this one is donating directly to the ring. It can perform resonance with the ring because the nitrogen has that lone pair right there. This carbonyl, it can't donate towards the ring. In fact, the ring would donate towards it. So we can maybe get an O- or something like that. We can't add anything to the benzene with the left structure. On the right, we could because that nitrogen that's connected to the benzene has that lone pair, but this carbonyl doesn't. It is when the nitrogen is directly attached to the benzene. It's a withdrawing if it's on the other side. Yeah, it's the same for esters too. So if an ester oxygen is donating directly to the ring, then that's good. But if it's on the other side, not directly bonded, then it's a deactivator. Do you mean like this? I don't know what you're asking. Okay. Maybe I can go over that at the end. All right, I'm going to go ahead and move on for sake of time. This next one, we have nucleophilic addition reaction. So whenever you're in your exam, make sure you're reading your test carefully. So nucleophilic addition reaction, we just did an EAS reaction. So maybe you're thinking, oh, NAS, okay. However, you'll notice that these are not benzenes. That's not a typo. These are not benzenes. They're just regular cyclohexyl groups. So this can't be NAS because we don't have benzenes that we're working with. So this is actually just asking us for nucleophilic addition to a carbonyl. So we know that nucleophiles, they're electron rich, so they want to attack something that's partially positive or fully positive. So we're not going to be doing like a benzene reaction. We're actually just going to be having a nucleophile of some unspecified nucleophile, and it would come in and attack our carbonyl because carbonyls are partially positive. And so you'll notice that in each of them, we have a carbonyl, a ketone, or an aldehyde of some form. And so we have to rank the reactivity of these ketones and aldehydes. So remember that we're looking for partially positive here. And so in the case of ketones and aldehydes, the partial positivity of the carbon in that carbonyl is going to be dependent on the R groups that it has next to it. So if it's attached to two R groups like a ketone is, then we'll have two like hydrocarbon groups or something else that donate their electrons towards that partial positivity just by induction. And so more R groups would make that partial positive carbon less partially positive, and therefore less reactive in this case. So say we want more. And I specifically say R groups. If you're asked something maybe like an acyl chloride, like James was just mentioning, a chlorine is actually withdrawing. It would take electrons away. So that would be kind of a different question. In this case, since we just have ketones and aldehydes, we're just kind of considering the R groups. So an aldehyde only has one R group to donate electron density via induction. So aldehydes are pretty much always going to be more reactive than any ketone. So in this case, we have less electron density donating towards that carbon, so it's going to stay pretty partially positive, and so it would be our most reactive for this type of reaction. So the middle and the right, we have a cyclohexyl, and then we have a methyl, and then on the right group we have 2 cyclohexyls. And so this is just kind of by size. So the more of our group that we have, the more it can donate electrons via induction. And that's just because there's more of them. So in this case, since we're looking kind of just at the difference between this side and this side, a cyclohexyl group will be donating more electrons to that partially positive carbon. So it'd make this more neutral. And we don't want neutral, we want positive. So this one is going to be our less reactive group. And then in the middle, again, it's just in the middle, so it'd be our number 2. Any questions about that one? Yes. Yeah. Okay. Gonna go ahead and move on. All right, so we love aromaticity. We love aromaticity. Okay, so aromaticity is kind of a complicated process. So I made a little cheat sheet for you guys. So this is kind of a stability question. Aromatic is going to be more stable, which is why at the beginning of the benzene chapter, you talked about how like benzene couldn't do any of these reactions that most molecules could. So aromaticity stabilizes a compound. Non-aromatic just means it's either not planar or non-cyclic, and it's just kind of in the middle. And then anti-aromatic is less stable. So it's kind of like a little ranking that we got here. So for aromaticity questions, most of them are probably going to be 2. They could potentially be 2. And so that'll depend on the resonance that you do. So in one resonance structure, maybe a molecule is sp3, so it would be considered non-aromatic, but in the other resonance structure, it could be sp2 and therefore aromatic. So if you're given a choice, you're going to go with the more stable option, because if it's a more stable option, the molecule is going to want to be in that form. So it's more common with like anti-aromatic versus non-aromatic. If you have an anti-aromatic versus a non-aromatic, the molecule is going to prefer to be non-aromatic because it's more stable than being anti-aromatic. So same concept, but yeah. So aromaticity works by the interaction of electrons in the same plane. So for benzene, there's like a little pi cloud that sits above the ring, and it's all these electrons in the same orbital, and they interact and make that molecule aromatic. So you'll have your 2 little rules, the number rules, and you can just memorize one, and then it's kind of just an easier way. So like 4n plus 2, if we get an integer value, so 1, 0 would count 2. So 0, 1, 2, whole numbers basically, including 0. That would be an aromatic compound with that formula. If we get a fraction, so like 1/2, 3/2, etc. With this formula, it would be anti-aromatic. If you're using the 4n rule and you get an integer, it'll be anti-aromatic, and a fraction would be aromatic. So you could just use one. Usually people just use the 4n plus 2 rule, and then if they get a fraction, they know it's anti. If they get an integer, they know it's aromatic. So you don't really have to memorize both, but there's the numbers. Yeah, so I kind of mentioned this. Not really, actually. So sp3 versus sp2. Whenever a molecule is sp3 hybrid, we have 3 sp3 orbitals that are on the same level. sp2, we have 3 sp2 hybrid orbitals and then 1 p orbital that's not in the same plane. So I have like a little drawing here. I tried to make it 3D, Hopefully you can see that. But in this one, the colored orbitals are going to be the sp2 orbitals, and they're all on the same plane. So pretend they're like flat on the same plane together. And then the p orbital is the one that's sticking up and down in the black. So yeah, again, these aromatic electrons, they'll all kind of have this p orbital that they interact with and make a molecule aromatic. So I'm just going to go ahead and do these examples. So one thing I didn't put on my little chart is that boron is always sp2. So boron is kind of a weird atom. It's fine with just having 6 electrons. So even if it has 3 bonds, it's fine. It's neutral. So boron will always be sp2. In this case, we have 2 of them. So we just know that those don't have any like lone pairs or anything. We know they're sp2, so this could still be aromatic or anti-aromatic. And so we're just going to count our electrons. So we have 2 for a lone pair, 2 for a double bond, and maybe a radical if you ever got one of those questions. Usually it's just double bonds and lone pairs. But in this structure, we have 4 pi electrons. All right, so our rule is, I'm going to use 4n plus 2. If we put 4 into this 4n plus 2 rule, we will get 10. No, wait. And okay, so yeah. 4n plus 2 equals 4. Sorry. So we get 4n is equal to 2, and then that gives us 1/2. So we don't get an integer value, so we know that this specific structure it does not satisfy the aromatic rule, so it would be considered anti-aromatic. So just make sure that you double check. I don't have any other lone pairs that I could resonate with. Again, boron is sp2, so it's not an sp3 atom to make it non-aromatic. So this one's kind of stuck being anti. So that's not very good, but there's no other structures that we could have. So in the middle, you'll notice we have a lone pair at nitrogen. We have some double bonds, and we have this oxygen that is double bonded to the ring. So in this form, we would not consider the double bond to oxygen in our electrons because it's not in the ring. Remember that aromatic, the electrons have to be in that ring. So if anything is outside of the ring, even this one, it's attached to the ring, but not inside, we would not consider those electrons. All right, so currently we have 2, 4, 6 electrons. All right, so that's pretty good. That's aromatic. I guess one thing we might want to check, nitrogen, we have 4 bonds right now. Could we potentially make that sp2? And the answer is yes. We can just resonate that nitrogen lone pair in the ring, and we get carbanion here. And then we'd still have 2, 4, 6 electrons. So this one is good in both forms. This one's aromatic. All right, for our last one, we have a cycloheptane. So we have 2 with our nitrogen, 4, 6, 8 electrons. Well, once you get the hang of this, you'll be like, okay, 8, that doesn't fit the 4n plus 2 rule. So this would be anti-aromatic. However, if we consider this nitrogen to be sp3, then that would make this whole structure non-aromatic. And so in this case, since we're between anti-aromatic versus non-aromatic, non-aromatic is more stable. So this molecule will kind of stay with that nitrogen sp3, and it'll be a non-aromatic molecule. Okay. Any questions on aromaticity? Yes, except for carbanions. So I'm going to get into that. Yeah. You can. However, so in this form, it's sp3, right? It's got 4 bonds, or 3 bonds and a lone pair. If we resonate it, it'll be sp2, so it could be aromatic or anti-aromatic. But in this case, since we're between anti versus non-aromatic, we would choose the more stable. So maybe in real life, this structure would just keep that nitrogen as sp3. So that's what I mean by you might have options. Yeah. Mm-hmm. Personally, I suggest like checking all of them. But yeah, typically. So yeah. Because in this form, it's the nitrogen is sp3. In the resonated form, so in the resonated form, now the nitrogen is sp2, so we could consider it to be anti or aromatic. If we count the electrons, we still get 8. So it's only between anti-aromatic or non-aromatic. There's not a chance for it to be aromatic. So we're just going to go with non-aromatic and keep that nitrogen sp3. So then to your question about, is it always going to be sp3 or sp2? It's kind of complicated. So I guess I will preface this by saying it may vary depending on your textbook, but for the purposes of this exam, I'm going to tell you. So if we look at carbanions and atoms that have multiple like options, like 2 lone pairs or a lone pair and a double bond, we have to look at the orbitals that we have. So for this first carbanion, we have A, B, C, and then a lone pair. So A would be kind of like off to the left, B, and then C. And so those ones would all be in that planar form, in that sp2 orbital. Because remember, we have 3 sp2 and 1 p. And then for aromaticity, the lone pair will be in that separate p orbital, so it can interact with the other p orbitals in the structure to do that aromaticity thing. On the bottom, we have a carbanion. Well, not a carbanion anymore. Now it's resonated and it's a double bond with B. So we don't have a lone pair anymore. But remember that double bonds they're kind of split in that pi orbital. So in this one, our orbital might just have 1 electron that it's sharing with the nearby p orbital. And so those would also still contribute to that aromaticity. In this case, they're split. It's not localized onto that carbon, but they would still contribute to that aromaticity because they're in that p orbital. So it's the same thing for atoms that have multiple lone pairs or a lone pair and a double bond. So I guess I'll do A, B, C. So we have 3 positions. We have the 3 sp2 orbitals, and we have the 1 p orbital. So even though we have 2 lone pairs, we can't consider both of them as contributing to aromaticity because only one of them can occupy the p orbital that does the aromaticity. So for this sulfur, I would just count 1 and not the other. And it's the same thing for a double bond and lone pair on the same atom. So we'd have our 3 that are in the sp2 orbitals. And then so then in this one, you can consider either, so like the double bond or the lone pair, but we'll only consider 2 electrons, not the 4 from both the double bond and the lone pair. So then for carbanions, it's kind of complicated. And again, this might vary depending on the textbook that you look at. But since this is the exam, I'm going to tell you what's on her exam. So for carbanions, you might come across a question like this, where we have 2, 4, 6, 8 electrons. And so you might be wondering, well, a carbanion has 4 regions of electron density, it has 3 bonds and a lone pair. So why wouldn't we consider this question to be non-aromatic? And so the reason is that for carbons, it's a little bit different than for a nitrogen or sulfur or an oxygen. So for carbons, the resonance stabilization will delocalize that negative charge. The planarity will also contribute to the stability of that molecule or the carbon. So a planar structure is better since there's less overlap between steric hindrance and other groups. And then in this one, we don't have any adjacent electronegative atoms, but maybe there's like a sulfur, or an oxygen, or a nitrogen, and that would also stabilize that negative charge. So for carbanions, they're pretty much always going to be more stable in that sp2 form. So a carbanion would always be considered sp2. So in this case, we can't consider it as sp3. It's going to have to be sp2. So we don't have the option in this case for a non-aromatic compound. Okay. Any questions on aromaticity? Okay. I'm going to go ahead and move on. All right, we've got our reactions. So this exam didn't have a Diels-Alder, but I included one at the end, so we'll go over that, but we'll just get started. So we have a OCH3 group, we have a benzene and a acyl chloride. So this one is going to be Friedel-Crafts acylation. So in this case, step 1, we are going to attach this part of our reagents to our starting benzene. And then OCH3 is a strong activator, and it's going to be ortho-para-directing. So we're going to put this carbonyl and benzene ortho or para to the OCH3. So sometimes there's a couple of options. In this case, all of those positions are free. But I'm just going to put the groups to be para, because that gives a little bit more room for that carbonyl. So sometimes steric hindrance is a factor that you need to consider. So just to be safe, I'm just going to put that carbonyl kind of in the position that gives it the most room. So then our second step, we have fuming H2SO4. This one is also SO3H2SO4. It's the same thing. So this one adds a sulfur group, sulfate, onto our benzene. So now we have 2 benzenes, so we have to figure out which one we're going to add this new group to. And so that's going to depend on which benzene has an activator on it. So this benzene over here, it just has this ketone, and ketones are withdrawing groups. They're deactivators. So we're not going to add our new group onto that deactivated ring. Kind of the ring that we started with the OCH3. Remember that OCH3 is an activator. We do have this deactivating group, but in this case, the activator will kind of win, and we'll put the sulfate group onto that ring. So again, it's the same structure as before. It's an ortho-para-director. Our para position is already taken, so we're just going to put this sulfate group ortho to that OCH3. Okay, so then that would be your final product. Questions on that one? Okay, moving on to our next reaction. All right, so we have this benzene with a couple groups on it. We have zinc mercury and hydrogen chloride. So this is what's called Clemenson's reduction. And this one is kind of a special reducing agent. It will not only reduce that ketone, it will reduce it all the way to be a hydrocarbon group. So we're basically just going to get rid of that ketone and replace it with some hydrogens. In addition, we have this nitro group. And so this reducing agent can also reduce that nitro group. So first step, instead of a ketone, we're going to have our just regular hydrocarbon group. And then this NO2 will be reduced to NH2. All right, so for our second reaction, this set of reagents is what's called a Birch reduction. So this one is also pretty special. It will reduce a benzene to be a cyclohexane with 2 double bonds instead of 3. And so this one is special because it specifically puts the double bonds depending on whether the group is an activator or a deactivator. And so in this case, activators, or for the type of reaction, for the Birch reduction, activators are going to be put on sp2 carbons if possible, and deactivators would be put on sp3 carbons if possible. And I believe she explains that mechanism in the notes. I'm not going to get fully into it right now. So in the case of a difference, if one is going to be forced to be something that it doesn't want to be, you will kind of choose the stronger group to be in the correct position. In this case, we can actually get both of those activating groups to be on the sp2. So this one kind of just works out nicely. Any questions on that one? Because this reducing agent is strong enough to react with that nitro group. Yes, there might be a case, let's say if we had the NH2 at that position, at the ortho to the ethyl, then you'd be forced to put one on sp2 and one on the other. One thing I forgot to mention, the double bonds have to be across from each other. Yes. It has to do with like the resonance of the ring and like the electrons going around and stuff like that. In this case, it didn't matter. Both of them could be on the sp2. But his question was, if you had to pick, we put the stronger activator on the sp2. And that was like if it was in that position instead. Okay, I'm going to go ahead and move on. All right, so this first reaction, this is what's called the Gilman reagent. And so what this one does is it replaces that chlorine on that acyl chloride with one equivalent of the R group that's attached to that cupric lithium reagent. So we have CH3, CH2 in parentheses 2, but we're only going to add one equivalent of that. And we're just replacing that chlorine. So the product of step 1 would just be, we replace that chlorine with a CH2, CH2, CH3. So now we have a ketone. This next reaction we have not learned yet, so I am going to skip it. I think this was from a previous year where she actually went straight to chapter 19 instead of skipping over it to go to the ketones and aldehydes. So I'm just going to skip that one for now because you don't know yet. I guess any questions on the Gilman reagent? Okay. Second page of our reactions. All right, so we have our Br2 and light. with our benzene. So remember that for Br2 and light, it's typically going to add that bromine to the more stable position. In this case, that's going to be right next to the double bond. I think for more recent exams, she typically uses NBS in light, but it's the same bromination reaction. So in this case, we're just going to be adding our little bromine right there. So step 2, we have Mg and ether. So this is classic. This is our Grignard. So we're just going to change that into an MgBr. And then this last reaction is a little bit different than our typical Grignard. So we have this nitrile, and we have our Grignard reagent. So what happens whenever we have a Grignard reagent react with a nitrile, we form what's called a ketone. I was thinking of the next question. So this is just going to change the nitrogen to be the carbonyl, and we just kind of connect the two together. So the Grignard would attack that carbon. So we have our carbon. It's going to have a CH2 and a CH3, and then instead of having a nitrogen, it's going to have a ketone instead. So this is another one of our ketone forming reactions. Any questions on that one? Mm-hmm. Yep. Mm-hmm. That the oxygen comes from the then H3O+. So in case you're wondering. Okay. Go ahead and move on. All right, so we have an alkene. We have our ozonolysis. So remember that ozonolysis is the milder splitting reagents, and it adds ketones and aldehydes, or it turns that double bond into ketones and aldehydes. So you notice that for this specific structure, we will form an aldehyde because we have a hydrogen that's on that double bond, and it's symmetrical, so we only have to worry about drawing one, but we have a 1, 2, 3, 4 carbon aldehyde. So 1, 2, 3, 4. And again, we have like 2 equivalents, but you don't need to write that it's 2 equivalents. And that was steps 1 and 2. So step 3, this is what I was thinking of before. So this is what's called the cyanohydrin reaction, or forming reaction, or whatever. So a cyanohydrin is whenever we have an alcohol and a nitrile kind of attached to the same carbon. So this nitrile, it's going to attack that partially positive carbonyl group. Our oxygen is going to be kicked out to be O-, and then later it get protonated to be the OH. And then we just have our nitrile attached to that carbon. So for our final product, we will have this alcohol and then the nitrile. Any questions on that one? What do you mean? Like, it has to be done after an aldehyde form, or what? Not necessarily. This is just like an aldehyde reacting with the in this case, I think they drew an aldehyde because they're more reactive. This would be like one of those nucleophilic attacks that we talked about in the back section. We did like a ranking with like the ketones and the aldehydes. So aldehydes are more reactive, so I think they just chose to do an aldehyde, but it would work with a ketone as well. In this case, the ketone would have the additional R group, but yeah, same thing, the OH with the nitrile. Yeah. Okay. Go ahead and move on. All right, so this one, unfortunately, we have a like synthesis kind of question. Okay. So in this case, we have to start with this and we have to end up at this. So sometimes these are kind of shorter questions. So sometimes it's easy to start from the left. Sometimes it's easier to start from the right. In this case, I'm just going to start from the left. So we want to get this to be a ketone at some point. So what we're going to do is we are actually going to oxidize this side chain and turn it into a carboxylic acid. So the way we can do that is we can use our Na2Cr2O7, H2SO4, and then in this case, we specifically have to use heat, otherwise it's not strong enough to react. And so what that reaction does is we have our benzene. This reagent will oxidize any like carbon side chain to be a carboxylic acid, a 1-carbon carboxylic acid, except if we have a tertiary group, because we can't oxidize a carbon that already has 4 bonds. In this case, this isopropyl has a hydrogen that we'd kind of use to start that oxidation process. That is a good question. I cannot remember. This reagent is typically for like oxidizing the carbon side chains, so just hydrocarbon side chains, but I can check after and see if it would react with any ether or not. I want to say no because you want that carbon to be there for that carboxylic acid, but I can't remember, so I don't want to say anything that's wrong. But in this case, we are basically going to completely cut off this isopropyl group, and then we're just going to have a carboxylic acid coming straight off of the benzene. So you could also do this with KMnO4, OH minus, and heat, but then you'd have to do a second protonation step. This one would form the deprotonated carboxylic acid, so you'd have that H plus step to turn that back into. So I'm just going to use the Na2Cr2O7 because it's just 1 step instead of 2. All right, so the next step, so we have a carboxylic acid and we want to turn it into a ketone. So we're not turning it into an ester, so unfortunately we can't do like another alcohol with H plus because that would make an ester, not just a regular ketone. So we actually have to do something kind of unique for this one. So what we are going to do is we want to do a reaction with a lithium reagent. So in this case, we want to form a, or we want to add on a propyl group. And so by using this lithium reagent, we can attach the R group to that carboxylic acid, and then we'd form that ketone. However, you'll notice that there are 2 oxygens, so you might be wondering how that OH gets removed. And so that's actually going to be by using 2 equivalents of this reagent. So yeah, so we just have to use 2 equivalents to make sure that we just get left with the 1 ketone. I'll put that. And then technically that one would form so I'm just going to draw the intermediate step for you guys. So we have our 2 oxygens. Eventually one of them is going to get kicked out to become, so that other oxygen can become the ketone. And so that's again why we use our 2 equivalents. So then to kind of fully convert it back into the carbonyl, we're just going to use H3O+. So I'll put it right. So for our first step, we oxidize that isopropyl side chain with our Na2Cr2O7 H2SO4 and heat. We got a carboxylic acid from that. So then we use this lithium reagent, and we form this kind of funky intermediate. And then we use two equivalents to make sure that we get both of those oxygens accounted for. And then our last step is just H3O+, and then that will reconvert that one of the oxygens into the ketone with that R group attached on. Yeah, so it does. In this case, we don't have an OH, so we're using it for a slightly different thing. But that's also why we use slightly different conditions. So the regular Na2 Cr2O7, it's just Na2 Cr2O7 H2SO4 and what, like OH or something? Yeah, so it's slightly different conditions. The heat is what makes it different from that reaction. And so that actually allows us to be kind of stronger and oxidize the carbon instead of like an OH. Yeah. If it's easier, you could use this set of reactions, although that's still kind of similar to our regular oxidizing. So yeah. Mm-hmm. No. So that's what she was just talking about. Jones oxidation wouldn't be strong enough. We have to like add this heat, but I don't know if like the Jones, because Jones is slightly different from the Na2Cr2O7, but as far as I know, the ones that we learn are just this one and the KMNO4 with like the heat. So. What do you mean letter or number? Oh, like NaCr2O7? I have no idea. It depends on how closely the TA is paying attention and if they're going to be that picky, but I really don't know. Yeah, I don't know. Some TAs might let it slip and some TAs might not. I don't know, unfortunately. I'm going to go ahead and move on. I also included a little Diels-Alder question for you guys. I think we did one last exam review, but I don't know, might as well. I also re-included this, so if you want to take a picture of it in a second, we can do that. All right, so we have our Diels-Alder. In this case, we're starting with a cyclohexane on the left, so we're going to eventually form a bridged compound. And so the way I like to do them is I like to first draw my little structure. So that double bond comes there, that one comes there, and then this goes back into its middle. So again, I've got this bridged compound because this part of the left molecule is still there. We have our new attachment to the dienophile. We have our double bond on the left. All right, so then for wedges and dashes, remember that anything in here is going to go in the wedge. In this case, it's kind of just shown by that 3D sort of structure. And then on the outside, this is going to be on the dash. So this carbon, we have an OCH3. And then this carbon, it's still on an sp2 carbon, so we don't need to draw a wedge or dash. And then for the dienophile, ideally, we want our groups to be on the dash. However, sorry, on the wedge. Yeah, on the dash, sorry. However, the two groups are not trans, but trans-ish to each other. So one of them is going to have to go on a wedge, and one of them is going to have to go on the dash. So in this case, since they're different, I'm going to put the bigger ketone group on the dash. And then the methyl, since it's smaller, I'm just going to put on the wedge. All right. So that's wedges and dashes. And then our last step is going to be our regiochemistry. So remember that that's our like 1, 2, 1, 4 rule. So we want the withdrawing groups and the donating groups from the diene to be a certain distance away. So we're looking at our withdrawing group here. I'm going to start 1, 2, 3. Okay, so that one's not favorable. 1, 2, 3. Okay, so that's not favorable again. So what I'm going to do is I'm just going to redraw it with my my ketone on the other side. So it's still going to be on the dash. I'm just putting it at a different position. We have everything else the same. Our CH3 on our wedge. And so now if we count, we get 1, 2. Okay, that's good. And then 1, 2, 3, 4. Okay, so that's good. So our final product would be okay, so that would be our final product. Any questions on Diels-Alder? I don't remember the key if they like specifically said that there has to be one on which, but my thinking is just that that group's bigger, so it's more preferable for it to be on the dash versus a smaller group. So I can't remember if like you'd get points off the other way, but I would strongly suggest doing it like this. If it was like both of that same ketone group, then it wouldn't matter. But there's just a difference in this one, so. The endo rule is the dash thing, yeah. For the dienophile groups. Okay. I'm gonna take a water sip, so if you guys want to take a picture of this real quick. Okay, I'm gonna go ahead and move on just a second. Okay. Just a second. Okay. I'm assuming everybody's done. Okay. All right, so now we've got our mechanism. So this one looks annoying. I think just because it's an older exam. So, we have to kind of attach these groups together in some way. So what we are going to do for our first step, and we have these OHs. You'll notice that we kind of attach our phenol to the other group at that carbon. So it looks like I'm going to want to form some form of like positive charge there somehow. So what I'm going to do is I'm going to deprotonate the, or sorry, not deprotonate. I'm going to have this alcohol steal a hydrogen from the hydrofluoride. I'm going to get this OH2 now. So that makes that OH2 a good leaving group, and so that's just going to leave. All right, so now I've got this positive charge, this carbocation. And again, we want to attach these two groups together. So I can now have my phenol attack that carbocation and do like an EAS reaction. All right, I'm just going to draw. We have our phenol. Our OH. All right, and then I want it to be para. So let me redraw this a little bit better. All right, so we've got this one. All right, so I want my new group, or this the benzene with the propyl group, to be para to our OH on the phenol. So I'm going to have this double bond attack that carbocation and kind of attach to that group. So we're going to draw attach here. So we will have our benzene. So we have our phenol. All right, so now we've attached that group. If you remember your EAS, you'll have to do this kind of big transition state resonance type thing. So this carbon gained that bond from the attack, so it's not going to be positive. It's going to be this one here that we're looking at on that other carbon in that double bond that's going to be positive now. So again, this is kind of just the EAS mechanism, so if you want to like review that, you could do that. But we know it's a benzene, so it's going to do all this resonance around that ring since it's aromatic. So we're just going to get a lot of transition states, a lot of resonance structures. So first, I can have this adjacent double bond come in. And the worst part about mechanism is just redrawing everything. All right. So now this carbocation is satisfied, but we have a plus charge at that position now. You could also resonate with that double bond, kind of keep going around the ring. So now we'll have double bond there, and a positive charge here. And then we just have to go backwards and maybe do the same one that we just took. So that's kind of those resonance structures. You'll notice that we do have a plus charge that's at the position of the alcohol. So what we can do is we can have the alcohol donate one of its lone pairs for another resonance structure. All right, so we've got that double bond, we've got that double bond. So now we have that resonance structure where our oxygen is going to be positively charged. And this is going to be the most important resonance contributor because we have all of our octets satisfied. So I think you could probably draw the kind of last few steps from any one of the resonance contributors, but I'd probably choose this one because it's the most stable. So we need to reform one of those double bonds in the benzene because we want it to be aromatic. So we're just going to do a kind of elimination reaction sort of thing. So we can take a nucleophile from the solution, so fluorine, maybe like H2O. And so this can take back its hydrogen. That hydrogen can donate to the benzene, but then we'll have to push that double bond, and then we'll have to push that double bond back to reform just our regular alcohol. So that will give us our final product. Any questions on this? Moving on to our synthesis. So synthesis is a little bit more tricky for this exam, so I highly suggest doing a lot of practice with it. You kind of have to take a lot of things into consideration. You have to think about like your activating groups, your deactivating groups, and everything like that. One thing that's kind of common on the synthesis is an ether forming reaction. So I'm going to use this as my kind of first step. I kind of want to split this molecule up into as many pieces as possible so I can kind of work on those benzenes separately. So for this first step, I want to split this group of benzenes and this third benzene. I want to split them up. And so what we can do is we have our group on the left, And then if we react a bromine with a phenoxide anion, so the O minus, we can do like a SN2 kind of reaction. So I split the group up here between the CH2 and the oxygen. So the left will have my CH2 and my Br, and then the right side will have my O minus, and then paired to that is the NO2. All right. So I'm going to start with just the right because I want to show you guys how we can make that O minus. And so the way that you can make this phenoxide anion, so the O minus on the benzene ring, is you're going to use OH minus, heat, and 2 equivalents. And the previous molecule that you started with is going to be another bromine compound. So this is not exactly an SN2 reaction because it's sp2, but these conditions, the first equivalent will replace that bromine with the OH, and then the second equivalent is to make that O minus, so that going forward, we kind of have an easier time doing this substitution. All right, so then here's where you kind of have to considering like your activators and deactivators. So I always forget to do this. Benzene, stable 1 carbon molecule, and then everything else. All right, so that's kind of crazy. So we kind of want to work this back to a benzene. So we have to get rid of these 2 groups on here. So nitro groups are going to be very strongly deactivating. So I'm going to want to remove that first. If I keep the nitro on and then try to add a bromine to it, it's not going to work because that benzene is deactivated, and so it's not going to do any reactions. Bromine is a slight deactivator, but it's a lot better than nitro groups. Another hint at this is going to be like your OP directing. So we know that nitro groups are meta-directing. Bromines are ortho-para directors. So if I want to get this substitution structure, I'm going to have the bromine on there first to direct the nitro to be ortho or para. All right, so going backwards, removing that nitro group, we're going to use our nitration reaction. So that will just leave us with that bromine on there. And then for the last step, let's see, we can just do our FeBr3, sorry. Br2 FeBr3 as our catalyst. And then that will be from benzene. All right, so we worked it back to benzene. We're good to go on that side. So now on this left side, we have to work this kind of bigger group back. So again, I kind of want to split this into as many pieces as I can. And I can do a Friedel-Crafts reaction. So we can have our AlCl3 over the arrow as our catalyst. I'm going to split that molecule up. So I'm going to want my acyl chloride on the left. And then on the right, I'm just going to have the CH2Br group. All right. So for the acyl chloride, we're going to have to use a reagent that will turn it into a carboxylic acid. In this case, we can use SOCl2. And then from here, we need to somehow get this 1 carbon carboxylic acid on here. What we can do is we can turn it back into an aldehyde and then do our Koh-Huckel-alkyl-Kuckel reaction to get it back to the benzene. So the Gattermann-Koch reaction. All right. So for this one, if we want to work it back to the aldehyde, and then back to the benzene, between the aldehyde and the carboxylic acid, we could just do a oxidizing reagent to do aldehyde to carboxylic acid. So typically we see it from OH to carboxylic acid, but you could still react an aldehyde and further oxidize it with Na2Cr2O7. In this case, we're just using the aldehyde, and are you talking about like the one that we looked at before? Yeah, so that was to turn a carbon, like CH3, into the, yeah, this one already has the oxygen on it. Yeah. So then we can just use our Gadamer Coke. So go co-huckle, alkyl, cocoa. And you can only use the Gadamer Coke to do the aldehyde formation on that benzene. You cannot do the one carbon phenol crafts because that the acyl, it's like acyl formide or something. It's not a stable molecule, so you can't use it. So we're good on that. I kind of did not leave myself any space. All right. So then we just have our CH2Br over here. All right. So we could just do our NBS light to remove that bromine. All right. So then we'd have our CH3. And so we can do the way we want to add that one carbon on. We could start from benzene, do our co-huckle alkyl cuckle, and then we could reduce the reduce that aldehyde to the CH3. And so we will be using the Clemmensen reduction reaction. So we looked at that in the reaction section. So remember that one's kind of special because it turns an oxidized group into just a straight carbon group. So we'll get our aldehyde, and then we already formed that, so we're good to go. Okay. Any questions? Okay, so before I do spec, we have a couple minutes. So it's just about time for anybody doing Ramadan to break their fast. So I'm just going to take like a 5-minute water break. I guess in the meantime, if you guys have any questions about any of the previous reactions, we can, or whatever, we can cover it real quick. Sorry? It said benzene or one stable. So the reason why she said that is because of this thing with the Gadamer-Coke reaction. So it's like this thing right here. So if you formed, or if you had that as like one of your reagents, that's not a stable one carbon molecule. Because a lot of people would like to just do Friedel-Crafts acylation to add this onto the benzene to form benzaldehyde. But this molecule is not stable and it's one carbon. So she's kind of like accounting for that in her instructions. So you can't be like, oh, well, it could form maybe and blah, blah, blah. So, yeah. So, yeah. So on the kind of middle, I guess. So we still did the Gadamer-Coke reaction, which is yeah, I know. Yeah. Yeah. So we do the aldehyde forming reaction, and then we use that to add that carbon onto the chain, and then we do the Clemmensen reduction to turn it just into the CH3. Yeah. So it's like kind of similar to this side right here, adding that one carbon. On the left, we just turn it into the carboxylic acid. On the right, we just turn it into the methyl group. In this case, we don't need to do that reaction. So with the harsh conditions was to turn a 1 carbon, or actually any carbon chain, to a carboxylic acid. Yeah. So in this case, we could just do the cohockyl alkylfuckyl to add the aldehyde. We already have something with an oxygen, so we kind of just further oxidize it with the regular stones. Yes. Yeah. Because if you just start with like a carbon, then like where's the oxygen going to come from? Like, so yeah. And you guys can ask questions about like the other sections too if you want during our little break. For mechanism? Yeah. Yeah, so this is an older exam, so the instructions are like slightly different, I think. I think she would prefer that you show the most stable contributor going forward with the mechanism. But you definitely have to show that one, the most stable one. Yeah. The fluorine is to remove the hydrogen as like an elimination, and then kind of reform that third bond in the benzene. I can find it real quick. Yeah, it was like H2 palladium and then like one other thing.
About the effects. I was saying like using the same effects like ranking. I was saying change it into instead of a freedom class, like these kind of questions, because people probably tripped over it. It's always going to be this number 3. Unless they change it into freedom graph species.
Was this on this exam?
No, this is it wasn't. I was trying to explain to if you change the question. So instead of saying
instead of EAS?
Instead of bromine in EAS, instead
of
Friedograms.
In EAS. Yeah, maybe we could do that at the end. I can't find it, but I can find it afterwards.
Which
It's the other reducing reagent that only targets the aryl position.
The aryl position, as in what do you mean by aryl position?
The one that's right next to the benzene, or the benzyl position, I guess.
NBS and lights is one of them.
No, like to reduce it.
To reduce it?
Yeah. Can't remember. Yeah, we'll find it afterwards. I know what you're talking about though. I'm pretty sure it's H2PD, H2 like platinum or something and something else. All right.
Give me this.
No, it's like if you have a ketone at like the benzyl position and then you reduce it and it doesn't target any other, but just the benzyl. Can't remember what it is. It might be in a later chapter.
Maybe so acetophenone, reduce it to like an ethyl benzene.
Yeah, but like specifically, it would only target that ketone position.
Wolf-Kishner. It's Wolf-Kishner. She has a role between Clemmensen reduction and Wolf-Kishner on my year, where you cannot use Clemmensen if you have a nitro group, and you cannot use Wolf-Kishner if you use it as a halogen.
Okay, James is saying it's Wolf-Kishner. But Wolf-Kishner? I think it's later.
It's way later.
I can't remember. Yeah. I'll find it afterwards. I'm probably just like skipping, like not seeing it in my notes. Okay, so we have our spec. And so I have the sheet that you'll see on your exam. This is just like your little charts. So remember that for spec, we always want to do our 2 times carbon plus 2 minus hydrogen all over 2. In this case, we will get 18 plus 2, which is 20, minus 18. So 2 over 2 gives us 1 unsat. So we have 1 unsat, which means 1 ketone, 1 double bond, something like that. And we have 9 carbons, 18 hydrogens, and 1 oxygen. So yeah, kind of unfortunate that we don't have a benzene, but it's okay. So we know we don't have an alcohol because there's no alcohol peak. We have this 1713. So this is our double bond region. So let's say maybe double bond, maybe a ketone. All right, for our proton NMR, you'll notice that we have 6 plus 1 plus 2. So this proton NMR only accounts for 9 hydrogens. And so we have 18 in our structure, so something's wrong. So anytime you do not have enough hydrogens in your proton NMR to account for all the hydrogens in your compound, you're typically going to have to multiply by an integer, and that just means that there's going to be symmetry. So in this case, to get to 18, we'd have to multiply everything by 2. And so that means that there's kind of like a plane of symmetry where the right half is the same as the left half. All right. So I just like to start with the alkyl section. So we have a 6H doublet. So a carbon can't have 6 hydrogens. So that means we're going to have 2 or 3 of the same group. So it could be either 2 CH3s or it could be 3 CH2s, because those would both give us 6. And then in addition, you would like double it to get the full amount. I'm just going to kind of think about it as 6 right now. Typically, I like to think of them as 2 CH3s first, because having 3 of the same CH2 groups is kind of less likely than having 2 of the same CH3 groups, if that makes sense. Kind of like a probability thing. So I'm just going to say we have 2 CH3s. I like to put them in a box, and that's my integrated number. And then the doublet refers to our neighbors. So if we have 2 neighbors, that means, or sorry, we have a doublet, that means we have 1 neighbor, because n plus 1 equals 2, so n is equal to 1. So that means we're probably going to have 2 of the same looking CH3 groups, both next to this CH group. Okay, moving on, we have our other 2 peaks. So the furthest we get is a 2.4. So it's it looks kind of different because it's kind of scaled differently, but we're still kind of in the alkyl region here. We don't have like a benzene, or we don't have a double bond, a carbon-carbon double bond in this case, because we're still in the alkyl region. So I'm just going to eliminate the carbon-carbon double bond as an option. In addition, we only have 1 unsat, so it wouldn't really make sense for us to have 1 double bond with a symmetrical molecule. And then the last thing I'm going to look at is I have this 211 peak. So if you go to the chart, that's like a ketone peak. So I'm going to say my 1 unsat is going to a ketone. And that accounts for 1 oxygen. So then going back to the remaining of these alkyl peaks, we have a 1H, and they specified that these are separate. So we have a 1H that refers to this peak. This is kind of just a multiplet. I can't really see like what the exact splitting pattern is. So I just kind of say M, and we know that it's a CH in a box. So And then this 2H peak on the far left, so we have a CH2. It's also got a doublet pattern here. So this is also going to have a CH2 neighbor, or sorry, a CH neighbor. All right. And so then we have all of our peaks accounted for. Remember again that we only looked at half of our structure with these peaks right here. So we'd like double it and consider us to have 2 of each of what we found for those peaks. So I'm just going to put all my pieces together down here. So I have this carbonyl. We had CH2 next to a CH, and then we had 2 of those because of the symmetry. We had a CH next to a bunch of stuff, and we had 2 of those because of the symmetry. And then our last peak was most likely 2 CH3 groups next to CH. We had 2 of those in our proton NMR. So with the symmetry, that means we'll have 4 of those after we account for that symmetry. All right, so these are all my pieces. So I'm just going to do a quick check and make sure it looks like I got everything. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So that's good. We have 1 oxygen. That's good. And then we have 2, 4, 6. 6 plus 12 is 18. So we have 18 hydrogens. So these pieces all account for everything that we need. So that's actually pretty good. And so now it's just kind of a matter of putting everything together. Well, we know CH3s kind of have to be on the end. So I'm just going to kind of start from there and work them in. All right, so we've got our CH3s. They're next to CHs. So it's likely that we'll have these CH3s kind of attached to the same CH. So maybe those 2 are on the same CH. These 2 are on the same CH. And then kind of working in, we have a couple of CHs that are next to a lot of things. So that's probably going to be right here. So this peak would be right here. In our splitting pattern, that makes sense. We saw that that one was a pretty large multiplet. So if we did the splitting pattern on that one, we'd already have a 6+1 with just those CH3 groups for each of those. So that's a pretty large splitting pattern. And then we know that we have a couple of CH2s next to a CH. So maybe that's like on that other side. And again, that would kind of just reconfirm that large multiplet for the CH. All right, so I've gotten this group, this group, this group, this group. I got my 2 CHs, and I got my 2 CH2s. So now all we have left is the ketone. So we're just going to throw that in the middle, and it looks good. If you kind of recheck the splitting patterns, everything should look good. We've got that symmetry, which means that, again, our splitting pattern is good. So yeah, any questions on that spec? Yeah, this is an old exam, so the formatting's a little different. It should just look similar to what you saw in your first exam. It should have the numbers. Hey, Yuki. I guess you guys are free to go if you want. Otherwise, I'll be here for a little bit to answer questions.